t, f, f equals 1 over t, and t is 2 pi square root of m over k. So, and then the opposite of that is going to be the 1 over 2 pi square root k over m. I gotta get used to erasing the board after each day so it doesn't get stuck on here like this.
Do you have this spray?
I think Miss Nakia has a spray, so I'll work on that a little later. Cause it's just the same. It's just the inverse. Because if it's normally f equals 1 over t, and t is 2 pi square root of m over k. So, and then the m over k. Yeah, so and then just doing the inverse. Yeah, so now it's just doing the inverse. And then since it's a mass of 9 times, all I would need to do is just put 9 times m. Cause k stays the same. And then it's just, yeah, k's, yeah.
Because it's a proportional constant.
Right. Yeah. Which, yeah, because we don't have any other values.
Yeah.
What would be the frequency of the oscillations in terms of F naught? Yeah. All right. So, last class we talked about simple harmonic motion. We looked at period, frequency, characteristics, simple harmonic motion, phase shift, writing the equations of motion for the system of a mass and spring undergoing simple harmonic motion, and then describe the motion of a mass oscillating on a vertical spring. Yeah, see, that's the same on a vertical spring, vertical motion. should be a yeah, because it should be the same.
Did you post the link on Discord on YouTube?
It's in the syllabus. Yeah, if you go to syllabus and then should be one of the first few sections. Oh, that other link is the college physics.
Oh, the college
Yeah,
physics.
that link. Yeah. Yeah, I was just putting down a link that you may be able to look at for something else. But I can put I can go ahead and put hours. So it'll be easier to obtain. Announcements. So our university physics. Okay, so I just put textbooks for this class. Alright, so that'll help. So now I bookmarked it so I could always have it. Alright, so this time we're talking about energy in simple harmonic motion. So we want to know how to describe the energy conservation of the system of a mass and a spring, and they explain the concepts of a stable and unstable equilibrium points. Let's do work. To produce a deformation in an object, we must do work. That is, whether you pluck a guitar string or compress a car's shock absorber, a force must be exerted through a distance. If the only result is deformation and no work goes into thermal, sound, or kinetic energy, then all the work is initially stored in the deformed object as some form of potential energy. So that's the big thing that we're about to look at is potential energy and kinetic energy. So this says, consider the example of a block attached to a spring on a frictionless table, oscillating in simple harmonic motion. The force of the spring is a conservative force, and we can define a potential energy for it. This potential energy is the energy stored in the spring when the spring is extended or compressed. In this case, the block oscillates in one dimension with the force of the spring acting parallel to the motion. So we get W, or work, which equals force times distance. So looking at the integral from initial to final of our x position with our force in the x direction in respect to x. So this is just saying that potential energy stored in the spring is this 1/2 kx squared.
The potential energy.
Potential. Yeah, potential energy is 1/2 kx squared. So that's all that's saying. It's just that the change in potential is initial minus final. Sorry, final minus initial. So and then if you use initial kx initial, and then you have the final kx squared final. So that's what that's breaking that into. Potential energy is 1/2 kx squared. So that's the big thing. So it's very similar between kinetic energy and potential energy.
And the potential, because the kinetic energy is when you move, right?
Right.
And the
Like, so, and then, the way,
Position.
yeah, that's what I was about to say. The way I like to think about it is, uh, what could happen, you know, if I say, oh, okay, it's getting further. I mean, even scientifically, we could say this is about x squared. You know, this is about our position. It has to do with our position. But then kinetic energy is talking about mass and then the movement of mass. So even explaining it scientifically, you see, like you're saying, it depends on position, how high up or how far away that displacement is for that position. And then kinetic energy is the change in the motion. So that doesn't really. In this section, we consider the conservation of energy of the system. The concepts examined are valid for all simple harmonic oscillators, including those where the gravitational force plays a role. So, and then we start talking about elastic potential energy, which is just the motion starts with all of the energy stored in the spring as elastic potential energy. And then as the object starts to move, elastic potential energy converted into kinetic energy, becoming entirely kinetic energy at the equilibrium position. The energy is then converted back to elastic potential energy by the spring as it is stretched or compressed, and the velocity becomes zero when the kinetic energy is completely converted, and this cycle then repeats. So understanding of the conservation of energy in these cycles will provide extra insight here and in later applications of simple harmonic motion, such as alternating current circuits.
So we're gonna have an elastic energy motion when we have a wrestle. What is it?
System,
Yeah,
like the
system,
spring system.
Yeah,
Mm-hmm. Exactly.
yeah, the spring system.
Exactly. Mm-hmm. How do you say it?
Wrestle.
Rosso?
Wrestle.
Risso?
Soar.
Sol?
Like soar.
Oh, soar?
Yeah, wrestle.
Rissor. Never heard of that one. Yeah, so this is explaining how you have the force moving. Right now the velocity is zero, but then once I have a negative velocity, then I'll have the 1/2 mv squared. And then saying negative because I'm moving in our opposite direction, our left direction, as what we say is positive. X will be to the right if there's a velocity moving to the right, 1/2 mv squared. And then right now the force is zero because it's completely compressed. Or even here is A is the amplitude, right, which is very similar to distance, right? Because it's saying x equals zero, which distance x equals the A, which is the amplitude. So amplitude positive A and then negative A. So that is what that looks like. So and then we're explaining the energy oscillates between the kinetic energy of the block and the potential energy stored in the spring. So we see U plus K, because like we said, there's some distance that we're at where there's potential energy, and then now that it's moving, now that there's some type of energy happening, some type of movement, then we're gonna have to add in the kinetic energy as well. So that's why we have 1/2 kx squared and then 1/2 mv squared. This is just saying the same thing. They're just breaking it down where x
participation. This is what
Right. Yeah, we're about to get to 1/2 ka squared. You know, it's more so like a derivation. It's more so just deriving to that point. You know, just saying the motion is defined by the position a cosine omega t plus phi or del plus phi.
oh, so, I think they're going.
Hey, great day.
How's it going?
Hey, peace. How's it going?
Good. So, yeah, a couple opportunities to get students some funding.
Hey, how's it going?
Not too bad.
Hey, great day. Welcome.
Absolutely.
Hey.
Oh, this is heavy, so I don't even
It's easy. See, look, you can see what this is.
Yeah.
That's what that's talking about. Yeah.
Woo, man.
Yeah.
But yeah, that's heavy.
Yeah, so this is our physics 2
Yes.
course. Right now we're talking about simple harmonic motion.
This is nice,
bro.
She's on course to graduate this semester, so
Mhm.
very proud of her. She's been working very diligently,
Mhm.
doing some small projects as well in chemistry. So working with some of the machines that hadn't been working for a long time, but her and a team of students are bringing it back to life.
Okay.
Do some things. So we're
What are you working on?
What do you mean?
Yeah, what are you working on?
Or am I working?
Yeah. What
Oh, yeah, I'm
what brings you to look
I'm
around?
just
and
trying to get some kids in the military. You know, anybody want their education paid for? I got them. They want more money for school? I got them.
Got you.
Yeah, I'm in college too, but not for this.
Yeah. Well, there's your advertisement.
I mean,
Is
I'm
it
sure
a
we'll
little
have
message?
stuff.
Yeah, absolutely.
And so his class typically starts with like 11.
Yeah, 6 for the next course, and then 11 in another class, and 18 in one of the other
That's the
online.
Yeah.
Yeah, but it's not too bad in person. In person, it's pretty nice class sizes. Yeah. So that one starts at 11.
Oh, good. But I just wanted to combine, meet some of the professors.
Yes, sir. What's your name?
Sorry, Vernil. Terrell. You can call me Terrell.
Sergeant Terrell.
Yeah.
Vernil.
Vernil.
Vernil. That's what's up. Yeah, nice to meet you. Yeah, you too.
All good.
Yeah.
Thank you so much.
Yeah, thank you. Well, there you go. There's some money there.
Yeah.
Some money.
Yeah, when you have the chance to do it,
Yeah.
if it's free, yes.
Yeah. I don't know if I'm able to. I don't know. Maybe with the sciences, like I wouldn't want to do combat for real, but there's some science positions in the military.
Okay.
Yeah.
You been out of military?
No. I've been to career days
Oh.
and the Navy and Air Force.
Oh.
They have science
Yeah.
positions.
Mm-hmm.
Yeah.
And they pay well. They have also
Yeah.
a lot of good, like,
Incentives,
Yeah.
benefits.
Benefits.
Yep. Yeah.
They gonna pay for school. When you
Mhm.
engage, they really gonna pay for school. They gonna pay for everything.
Yeah, I think it's like they do like a I believe some people have told me that there's a 2 years on and then 2 years off, something like that, like 2 years in school and then 2 years served, or the other way around, or like 4 years or something, 4 years served, or 4 years in school and then 4 years in the military, something like that.
I'm just gonna try to mention my grade up so I can still have my FAFSA pay for school.
Mm-hmm.
I wanna do that.
Yeah. Not a huge fan of the military complex that we have. Yeah, there's a lot of. Yeah. Yeah. So the next one. So this one, closer look at the energy of the system shows that the kinetic energy oscillates like a sine squared function, while the potential energy oscillates like a cosine squared function. However, the total energy for the system is constant and is proportional to the amplitude squared. So this figure shows a plot of the potential kinetic and total energies of the block and spring system as a function of time. Also plotted are the position and velocity as a function of time before time of 0. The block is attached to the spring and placed at the equilibrium position. Work is done on the block by applying an external force, pulling it out to a position of x equals positive a. The system now has potential energy stored in the spring at time equals 0. The position of the block is equal to the amplitude. The potential energy stored in the spring is equal to U equals 1/2 Ka squared. And the force on the block is maximum and points in the negative direction. Fs equals negative Ka.
To the negative direction?
Yeah, because this is saying the force on the block is maximum and it points in the negative x direction. So up here, when it's like this, you know, its position is at its maximum, but the force is pointing inward because that's where toward the equilibrium point. That's the main key for that, is that it's toward the equilibrium point. Like when we go further, oscillations about an equilibrium position. So it has a lot to do with this equilibrium position. So if I'm in a bowl, so this is explaining this. If we're in a bowl, then we're going back to the equilibrium point no matter which way we go. You know, if I move the bowl, you know, it's always going to want to go back to the equilibrium point. But then this one's saying, you know, equilibrium is still important, but because of the conditions, this is going away from the equilibrium point. You know, this one way is going toward the equilibrium point, but then if I had more force directed in that way, then it's going down. It's going away from the equilibrium point. So that's still the same with our spring and our energy. There's an equilibrium point that the system wants to revert back to. You know, it wants to be in simple, how could I say, like, it wants to go back to the equilibrium point. Yeah.
I always want to go back to that. This is the sign one, I remember the sign, the one on blue. And
Yep.
which one is cosine?
Yeah, so cosine starts at 0,
That's 0 and
but then sine starts at positive 1. So,
really, I can imagine how sine and cosine are related to physics. It's very weird for me to just picture it on my mind.
yeah, the best way I like to think about sine and cosine are the frequencies, like one of which that we can hear are each other. You know, we're vibrating at these frequencies, and then you're able to pick it up. So there may be like sounds that collide. There's in music, there's something called a sine wave, where it just stays the same. So maybe cosine maybe there's a cosine wave that changes. Examples. Real world examples.
Yeah.
Real world examples. So in the real world, cosine and sine functions are used to model periodic phenomena like ocean tides, sound waves, light waves, the swing of a pendulum, seasonal temperature fluctuations, and the rotation of wheels. Essentially, any situation where a repeating pattern of movement occurs back and forth can be described using sine and cosine functions depending on where the cycle starts. So maybe that has to do with it, depending on where the cycle starts. So maybe if there's a zero, if it starts at 0 and then goes up, or if it starts like maybe with me being a drummer, maybe the sine wave would be like when I hit the drum, because it's a automatic, that bead is like automatically registered as a frequency, already as a note, and then goes and then dampens, as opposed to something that might, I don't know, maybe like an earthquake or something. Maybe it starts from 0 because it's already at equilibrium for the world. We have a resonance tone, a resonance frequency that the earth is in. So it makes sense for it to be 0 and then oscillate and then,
Yeah, that was my
peak.
question. How do they gonna know that start at 0 or at 1?
Yeah. So I could see with musical instruments. Graph of sine. Sine are commonly used. More real-world examples include heights according to angles of depression and elevation. Here's an example of a sine wave. The electricity produced by the power company is a sine wave. Cell phones, televisions, and radios all use sine waves broadcast through the air. And then for cosine, law of cosine used in engineering to calculate distances or angles of elevation while constructing bridges or telephone poles, navigation pilots or sailors. Yeah, so cool, good question.
Thank you.
Yeah, so that's that, and then there's a total energy that's constant, because it's potential plus kinetic. Alright. So that's that. Equilibrium. So that's why it's talking about stable equilibrium point and unstable equilibrium point, and then the unstable equilibrium point. Stable, unstable, unstable. So, and then now that I think about it, there may be some certain types of sounds that are more unstable, like more